Okay, the last part of spring systems and such as is to talk about the energy transfers that actually occur inside those. Let's just clear this off. So we have we'll do a spring, and the energy stored in this spring, so the potential energy is a half kx squared. So if we have a spring that's oscillating according to what the equations we looked at before, if we have an amplitude A of an oscillation, then the total energy in the spring is going to be equal to a half k of the amplitude squared. So that's the total system. Now that is going to be made up of two components, and assuming there's no damping, in other words that it's a perfect spring, everything's perfectly elastic and so on, no energy is lost, we could sketch that this way. So just some kind of energy, and in this case it's restarting that graph. Energy in the middle. This graph looks a little bit strange because it's got two arrows. It goes to minus the amplitude to plus the amplitude. The total energy of the system is, let's just use a straight line for this, here. So this is E total, and at the negative amplitude its kinetic energy is at its maximum. Sorry, its elastic energy is its maximum, and similarly at its maximum amplitude, all of this, so this is the potential, elastic potential energy is in this color. At this point here, and at this point here, the velocity is 0. We look at the velocity graph over time, we're talking about these locations here as it's changing direction. So what's actually happening is exactly the opposite. Should go meet here. Should go meet here. Now, if we take at any given point in time here, this is about halfway in between, where half the energy has been transferred and half the energy is still stored in the spring. These two add up, so the kinetic energy plus the potential energy becomes E total. And at no point in time will that become bigger than this value here. So E total in the system is equal to the potential energy plus the kinetic energy. Right, if we now rearrange this equation, then the kinetic energy at any given point, if we know its displacement, where the kinetic energy is expressed like this, and the total energy is this, the rest is going to be the kinetic energy. So we have a half Ka squared. That's the total amount of energy in the system, minus a half Kx squared, which is the elastic potential energy at a given displacement. If we rearrange this equation, just factorize it, a half K comes out, and we end up with A squared minus X squared. This is quite an important point, but just make sure that you're comfortable with the steps in between these two. We're on year 2 now, so I'm not going to show you every single step involved. Now we also know that the kinetic energy is equal to a half mv squared. So let's just make a little bit more space here, and I'm going to change the colors. What we're going to do is just look at this part here. We're going to try and work out what the velocity is at a given point, depending on where we are in the energy exchange between the two systems of transferring from elastic potential energy to kinetic energy. Turns out to be quite easy. We rearrange that equation, divide both sides by, so V is equal to, the halves cancel, and we end up with K over M now, because, as we've seen in previous film, omega squared equals K over M, we can say that V squared equals omega squared A squared minus X squared, which, if we take the root out of both sides, gives us V equals plus or minus omega root out of A squared minus X squared. Now notice when V max is, just to compare this to what we already know. Now the maximum value over here is when it's the amplitude alone. So it's when x is 0. So we get V max equals omega A. And that is something that we've seen before. And just to remind you, that is because we had this equation, there happened to be a minus in front of it. There is obviously a plus minus here already. Minus omega A sine of omega t. When that is a actual value of 1, V becomes omega A. So we've seen this before, but with this case we've actually just derived that information using energy exchanges. This concludes the discussion on simple harmonic motion and rotary dynamics. We will talk about damping, but we'll do that in class.